Alright guys, so we see that we are currently on question 1993, question 1. This is the second question in your packet, and we see that we've got a new looking graph. And we see that this graph is scale reading in newtons versus time, which is different because all we've been dealing with is the acceleration versus time, velocity versus time, and distance versus time. So we have got this student that normally weighs 500 newtons, and so normally weighs that. So that means that this student's mg is going to equal 500 newtons. Okay? And so the first thing that it asks us to do is draw a free body diagram. And we see that the only forces acting on this student in the elevator is this normal force right here and this mg right there. So, they just told us that this person's normal weight is going to be this 500 newtons. All right, so the first thing that it wants us to do is calculate the acceleration A of the elevator for each 5-second interval, and we can see that for each 5 seconds there's a different scale reading. So for this first 5 seconds, we see the scale reading is 500 newtons. Now, the scale reading, you guys, is going to be this this normal force right here, because we see that it's changing. It goes from 500 to 700, back to 500, and then down to 300. Now, does our mass ever change? No, it does not, unless we eat a lot of Twinkies. And then we've got gravity. And gravity, the acceleration of gravity never ever changes either, unless you go to the moon or to Mars. So we put together this equation. The sum of the forces equals ma, which equals normal minus our mass times our gravity, or our weight. All right, and so basically what they want is to find this acceleration. What is the acceleration at each of these 5-second intervals? So let's go ahead and get a by itself. Let's divide our mass by both sides. Now, they don't directly give us mass, they do give us mg. So we can find our mass by dividing g by both sides, which is really 10. So we get 500 divided by 10. Oops, you can see that. And then we get 50 kilograms. So that is going to be the mass of that person right there. And so let's do this for these first 5 seconds. All right, so let's say from 0 to 5 seconds, we have got this equation right here. So we're going to say normal, which we see, this is the scale reading. So this scale reading, you guys, is going to be our normal force, because it's going to be changing. And we see that whatever force is pushing up on us is the force that weight scale is going to be reading. And so from 0 to 5 seconds, our normal force is 500. So we're going to say 500 minus our mg, which we also know is 500, divided by our 50. And we see that means we get 0 all over 50, which is just going to equal 0 meters per second squared. So that's going to be the acceleration for the first 5 seconds. So we're going to write that down right here, 0 meters per second squared. All right, now let's look at the next one. Let's look at the next interval, which is from 5 to 10 seconds. And we see that from 5 to 10 seconds, we have got this normal force of 700. So we're going to go ahead and say 700 minus 500 divided by 50. And so that means we get this 200 divided by 50, cross out our zeros, is going to be 4 meters per second squared. All right, and so I'm running out of room because I'm writing really big, but we can just come down here and continue our work. So then for the next 10 to 15 seconds, we're going to use the same formula, and we see that 10 to 15, we go back to 500. So we're going to say 500 minus 500 divided by our 50, and so we see, again, we get 0 meters per second squared. And so let's not forget to write down, so we've got 4 meters per second squared, 0 meters per second squared, and then now let's do for the 15 to 20 seconds. All right, so from 15 to 20 seconds, we see that we are at the scale says 300, so our normal weight is 300. And so now let's say, so from 15 to 20 seconds, we have got this 300 minus the 500 divided by the 50. And so we end up with negative 200 divided by 50. And so we end up with negative 4 meters per second squared. So we write that down in our next, so negative 4 meters per second squared. So we see, now we've got that, and this makes sense, because let's think about an elevator. So right here we know our elevator is just kind of standing still. It's just, and then we see that this is actually the elevator going up, because when you jump on an elevator, when you're trying to go up, it's a lot harder to jump up, and that's because the elevator is pushing on you. And so then we go back to our normal weight. So this is probably when we get to that second floor or whatever. And then let's say we press down. So this is the elevator accelerating downwards, because remember, when you go down in an elevator, you can jump up really high, and so you don't feel that force as much. The normal force is not as great. All right, so now that we have these 4 points, we can do the next thing it says. So plot acceleration is a function of time on the following graph. So this graph is going to be this one right here. So let's use these points that we just found. And so we know from 0 to 5 seconds, oops, I just wrote on the wall. Okay, so from 0 to 5 seconds, we are going to be at an acceleration of 0 meters per second squared. Then from our 5 to 10 seconds, we're at 4. So let's go up to that ticker mark where it says 1, 2, 3, 4. And so let's make a straight line across like that. And then we go back to 0 meters per second squared. And then now it's negative 4 meters per second squared. And so we've got that line right there. So this is what our acceleration versus time graph is going to look like. Now, tells us to determine the velocity of the elevator at the end of each 5-second interval. So that is what we are going to be doing now. So looking at this graph, we see that we have an acceleration of 0, but we must be moving some velocity. Or actually, we're not moving any velocity right there. But so let's go ahead and look at the first 5 seconds. So for the first 5 seconds, we have got our initial velocity is going to equal 0 because we begin at rest. And also it tells us that in the beginning. And so we want to know what is going to be the final velocity after that 5 seconds. All right, so we know our initial velocity is 0, so what's our final velocity? And we can use that really easy, really fun kinematics equation of V equals V naught plus AT. All right. And so now let's plug that in. So we get 0 plus, our acceleration is also 0 times our time, which is going to be 5. So now we end up with a velocity equaling 0 meters per second. We can write that in our little blank right here, 0 meters per second. Don't forget your units. Nobody likes naked numbers. They are shameful. So we now are looking at, so what's now the velocity at 10 seconds? We saw the velocity at 5 seconds is 0. Now we want to know what is the velocity at 10 seconds. We know again our initial velocity equals 0 meters per second, and that's because our final velocity at 5 seconds is 0 meters per second. So our initial velocity is going to be 0. We want to know what is that final velocity at 10 seconds. So we have our V equals our V naught. We're going to be using the same equation right here, but we're not going to write it out again because I trust that we know this by now. We know that our initial velocity equals 0 plus our acceleration, which now we have a positive acceleration. It is going to be 4 times our time, which is 5. So now we've got a velocity of 20 meters per second. We're going to write that down in our little box right here because that's what it tells us to do. So it says indicate your results by completing the following table. So that is what we are doing. All right, so now let's look at the end of 15 seconds. So this time, what's our initial velocity going to be? Well,